Yes. Donc bonjour à tous. Je suis Sandrine Antin, donc je vais présider ce jury. Et avant de laisser la parole à Jonathan qui va nous présenter ses travaux de thèse sur la climatologie et l'impact des rivières atmosphériques en Antarctique, je vais introduire le jury. So, good afternoon everybody. So I'm Sandrine Antin and I will chair the jury here. And before to let the floor to Jonathan, who is going to present his work, his PhD work on Antarctic atmospheric river climatology and impacts, I will introduce the jury. And if you don't mind, I will introduce the jury only in French, otherwise it will take too long. Thank you. And so I propose to the member of the jury just to make a sign to say, this is me or this is not me. Okay, this is me, okay. Donc cette thèse, les soutenances de thèse, donc les thèses doivent être lues par deux rapporteurs. Donc le premier rapporteur qui est une directrice de recherche au CNRS, donc Masa Kageyama. Can you sign? Okay. Donc Masa, elle est directrice de recherche au laboratoire des sciences du climat et de l'environnement à Paris. Elle est climatologue et spécialiste des paléoclimats et étudie les interactions climat-cryosphère. Le deuxième rapporteur, donc John King, qui est research scientist au British Antarctica Survey à Cambridge. Il est spécialiste du climat en Antarctique, en particulier dans les processus de couche limite. Il a publié en 1997 un livre avec John Turner sur Antarctic Meteorology and Climatology, qui semble faire encore bien référence dans la communauté scientifique. Un des examinateurs est donc Jean-Louis Dufresne, directeur de recherche au CNRS, au laboratoire de météorologie dynamique. Il est modélisateur du climat. Il est un des lead auteurs du groupe 1 du GIEC et il s'intéresse à l'Antarctique depuis quelques années où il fait même des missions régulières, même comme modélisateur. Ça, c'est à noter. Donc, l'équipe de supervision de la thèse est constituée de deux personnes. Donc, Francis Caudron, voilà, qui est professeur à l'université Pierre et Marie Curie à Paris et au laboratoire d'océanographie et du climat. C'est un modélisateur du climat aussi, avec un intérêt particulier pour les circulations aux hautes altitudes. Et enfin, Vincent Favier, donc, est physicien adjoint à l'IGE. Il aime beaucoup observer la neige qui tombe, ce qui le rassure particulièrement, notamment pour l'évolution du bilan masse en Antarctique. Donc moi-même, je suis Sandrine Antin, je suis directrice de recherche au CNRS, également à l'IGE. Je suis hydroclimatologue. Alors moi, quand je parle de précipitations, c'est plutôt des précipitations liquides. Et les terrains que je fréquente sont plutôt habités par des sociétés humaines qui sont de plus en plus vulnérables. En bref, je ne connais pas grand-chose à l'Antarctique et donc j'ai l'honneur de présider ce jury. So Jonathan, I will let you the floor for 45 minutes of presentation. And then it will be the classic session for the questions.
All right, very good. Set up here, but I'll first confirm that the jury can see and hear me before we start. So go to the Zoom here, share screen. Yes, that needs to be done here. So now everyone should be able to hear and see me. Yes, I get a head nod from Francis. All right, good. All right, then let's begin. So thank you, Sandrine, for the introduction. And so with that, let's begin the presentation for today. So for today's defense, I will be presenting my research on Antarctic atmospheric river climatology and impacts. I have the jury here, but as Sandrine already introduced, I will proceed with the presentation. Starting now. So where we are going to be today is Antarctica, coldest, driest continent on the planet. And it is considered a polar desert comprised of a grounded ice sheets and also floating ice shelves on the margin. Now, Antarctica is a desert because of a massive polar anticyclone that sits over the continent, a feature that has been known since the heroic age of Antarctic exploration way back even in 1915. But this presentation begins with a story. It begins in early January 2016 here in West Antarctica. During this time, I was working as a weather observer for the United States Antarctic Program. Here I am doing Antarctic science things. And so specifically, we were in Waste Divide Camp. It was a former ice core drilling site. So it has a very high elevation and also a very cold mean annual temperature of around minus 30 degrees Celsius. But in early January of 2016, it was not so cold. In fact, it was downright balmy, in fact. During this 1 week, 2 week period, temperatures were around the melting point at the camp, which was actually unprecedented for anyone's memory at that site. And during this time, we also had these very dark, ominous clouds sitting over the camp. And thanks to a research project that was measuring the cloud properties at the time, we discovered these clouds were full of liquid water, which is very unusual because most clouds at this elevation are a more clear crystal-like structure. So this was a very bizarre event that was not just restricted to this location in Antarctica. In fact, looking at the time series of temperature during January, we see Waste Divide here, and the temperature just almost reaches zero, a bit lower in elevation. The temperature did actually go above zero at Bird Camp. And this was something that was occurring all over West Antarctica, where widespread melting conditions were observed. Here, the star, looking at this map here, we see Antarctica in the center of this figure, and the star here is the location of Waste Divide. And during this event, when we look at the temperatures in the mid-levels of the atmosphere, and here we're looking at the polar jet pattern, we see an intrusion of warm air stream into Western Antarctica. And the jet pattern was this very meandering jet, as opposed to the more circumpolar jet that surrounds the continent. So because of this pattern, basically we had a period of 1-2 weeks of very warm, moist air causing melting conditions over this part of the continent. So this was a very remarkable event. And after the season ended, working with a team at the Bird Polar Research Center, we wrote a paper about what occurred during that 1-2 week period. But still, I had some questions about how to really describe the synoptic meteorology of what was happening during that time. So after that, I would come to Grenoble to start my PhD. And the PhD topic was about studying the circulation and storm track around Antarctica and how that might affect the mass balance of the continent. So with this in mind, I wanted to kind of revisit this topic and see what was happening in early January of 2016. So when we look at the satellite imagery from that event here on January 10th, instead of seeing what I expected to see like a very pronounced extratropical cyclone near the continent, to create the precipitation and to bring in the warm air. But instead, what we saw were we had two cyclones sitting off the continent, and then you have this filament of clouds streaming into the continent, and looks like a literal conveyor belt of moisture arriving from like the from the lower latitudes to the higher latitudes here. And this cloud signature looked familiar. It reminded me of what is classified as an atmospheric river. Now, atmospheric rivers are more commonly known in the mid-latitudes. They're quite famous, actually, in the western parts of North America. And they're notorious for their abilities to transport large amounts of moisture from the from the tropics and subtropics to the mid-latitudes. And when they actually arrive at a landmass, this moisture becomes orographically lifted and generates huge amounts of precipitation. So to kind of go over more what atmospheric rivers are, we can look at satellite imagery to give us some more clues. Now, atmospheric rivers are kind of recent to the nomenclature of meteorologists. It wasn't until they had satellites that can actually resolve the water content of the atmosphere. So here we're looking at the content of liquid water throughout the whole atmosphere. And the darker colors are where the moisture is very high. And what we've noticed is that you have lots of moisture pooled near the equator, where it's very warm and humid, so as we expect. But what catches the eye is that you see these filaments of moisture streaming through the oceans, through like the Pacific here, and occasionally hitting land masses. And when we look in the southern hemisphere, we see the same thing, and some of them even get close to Antarctica. And so these little streams of moisture, what became known as atmospheric rivers. And despite the fact that these rivers only cover about 10% of the Earth's surface, they actually represent 90% of all the poleward moisture transport. So they really play a very important role in the hydrological cycle of the planet. And to get into some more details about how the dynamics of the atmospheric river works. So typically here, we're looking at your typical extratropical cyclone structure. But the river is an independent feature that is typically found ahead of the cold front, here embedded in the colors orange and red, which represent the vapor transport during the storm. But they're not always associated with the extratropical cyclone. In fact, 20% occur without this sort of structure nearby. But when they do occur, they can actually lead to the explosive cyclogenesis and making storms much more powerful. And even sometimes the rivers can outlast the storm. So multiple extratropical cyclones can basically maintain the atmospheric river. And this helpful graphic here from the folk at the Weather Channel actually does a quite good job describing how the moisture is transported through the atmosphere. So we see moisture coming across the Pacific Ocean here, and then it encounters what's called a blocking ridge, a literal roadblock in the highway of the atmosphere. What it does, it redirects the moisture, which would have been heading west to east, directly into the higher latitudes. And this is something that's quite important for transporting moisture, let's say, to Antarctica. Now, what are some of the impacts, though, of atmospheric rivers? So in this example here, in March of 2015, we're looking at the water vapor of the atmosphere. Shaded darker colors are very moist here. And we see this atmospheric river deliver huge amounts of moisture to the west coast of Chile. Now that's where the Atacama Desert is, which is actually the world's it's actually, I think, the driest desert in the world. And when this happened, it delivered catastrophic flooding to the region, which was a huge loss economically. And at the same time, though, when we look at this image here, you see the river hit Chile, but also there was another river heading towards Antarctica, which was very curious, and we'll get to that one later. So that's for flooding potential, but other research in polar regions has shown previously that the rivers can also cause melting of the sea ice, and this was the case for the Arctic. What happens is the river can travel across the landmass, in this case, Siberia, and then it encounters a cold dome, like cold air sitting over sea ice. It's deflected upwards where it releases its moisture, and that moisture then can cause warming at the surface. Now for Antarctica, though, the only study prior to this PhD about atmospheric rivers came from Irina Gorbaskaya. So in this study here, she looked at a case study of atmospheric rivers hitting what is known as droning moorland, Antarctica. So here she's plotted the water vapor content of the atmosphere. And in red here, she's developed an algorithm that actually detected these atmospheric river events making landfall, and one in 2009 and one in 2011. And those two events were very consequential for that region. Those two events actually accounted for most of the snowfall accumulation in this 4-year period. Here we can see the red circles showing when the rivers had occurred, and then no snowfall for a while, then one here, and another major river here. So they were very important for the snowfall accumulation at this one particular site. So why does this matter, though? Who cares if it snowed a lot once in Antarctica over this 2-year period? So with Antarctica, we're very concerned, and we study a lot, what is called the mass balance of the continent. A mass balance is basically, what happens when you take your inputs, which in this case is snowfall, and then you have your outputs, or when the snow leaves the continent. Now, a mass balance is made up of a couple terms to simplify this. You have the surface mass balance, which is everything that occurs on the surface here. So you have your snowfall that accumulates on a continent, adding to the mass. Snowfall could then sublimate or melt and therefore lose mass. But once the snow actually gathers on the surface, then it becomes part of the ice, and that ice then flows to the margins of the ice sheet, where here, which is very common in Antarctica, it encounters an ice shelf. And the ice shelf acts to sort of be a buttress or kind of slow down the flow of ice from the continent into the ocean, which this is referred to as the discharge term. But the ice shelves are sensitive to melting at the surface or melting from the oceans. So but the idea is if the continent is in balance, then there's nothing to worry about. However, this is not the case. Antarctica has been melting, as we've all seen in the news. Here we're looking at the mass change in Antarctica since the early 1990s. And we can see in the purple here that Antarctica has been losing mass and has been causing the sea levels to rise. Now, most of this mass has been driven by losses of ice in West Antarctica. However, in the yellow here, we see the ice has been either steady or even slightly increasing during this period. And that has been because of increases in snowfall. This figure here from Medley and Thomas, we see that this red line here represents the accumulation of mass in East Antarctica, which has been caused by snowfall. And this accumulation in mass has actually mitigated some of that sea level loss, actually about 10 millimeters to be precise, during the 20th century. So going back to our mass balance of Antarctica, we look at a basin by basin basis. We see here the loss in mass in West Antarctica, as we've been hearing a lot. But in this corner of Antarctica here, in adjoining Montland, there's been a rather reasonable increase in mass. Now, this region here is important because in that study from Irina Gordovskaya, she pointed out that there were two atmospheric rivers in 2009 and 2011 that really accounted for most of the snow accumulation in that region. In fact, that accumulation really put a huge positive bias on the overall surface mass accumulation for this area since 1980. So we already see that atmospheric rivers can be a very positive term to the mass balance. We know that they can also contribute to melting theoretically, because they've been shown to do that over sea ice. And there's also the problem of the ice discharge. We know that the ice shelves are very sensitive in Antarctica, and that their loss could increase the rate of mass loss into the ocean, increasing sea levels. But what causes the instability of the ice shelves is actually something we have rather low confidence in this moment, at least according to the most recent IPCC report. So all that said, it made me realize that if I wanted to answer the question of the PhD, I should focus specifically on atmospheric rivers. So it leads to a series of questions and to how to tackle this problem. First, we need a way to track the atmospheric rivers. And with a method of tracking them, we can then create climatology over the most recent satellite period over Antarctica. And once we have that climatology, then we can get into the surface mass balance and the mass balance problem overall and study components of that. We can look in the surface melt, we can look at ice discharge, and we can also see for the increase in mass, see how they're affecting snow accumulation. So from here on, I've actually put little in parentheses here. This is going to help you follow along where we are going forward in this presentation in the bottom right corner here. So when we look in Antarctica and we make a map of the moisture transport in Antarctica, here I plotted a map of the water vapor around the continent. And I've highlighted here in red little areas of a very extreme water vapor in the atmosphere. And if we play this animation forward, you can see these little red areas, they're quite disorganized, they bounce around, they don't really show much coherence. However, though, in this example in early January, we see actually them, these areas of extreme moisture content form a coherent shape. This was actually early January of 2016, the event that gave all that clouds and moisture to Waste Divide where I was. And we could take this shape and actually train an algorithm to consistently detect other events that look just like this. So that's kind of the basis of creating an algorithm for detecting atmospheric rivers. But why did I need to make my own algorithm? There actually are algorithms that already exist to detect atmospheric rivers around the world. One of the more popularized ones is the one from Grenoble, which works over the whole globe. But this research from Irina Gordoevskaya has shown that a global algorithm might actually overrepresent atmospheric rivers around the continent. Here she's plotted the occurrence of rivers during the summer months and the winter months in Antarctica, according to the two algorithms. The bottom ones here are from the polar specific algorithm that she developed. And then the upper line here is from the global algorithm. And what we see is the global algorithm detects these rivers at a rate of almost 100 to 300% more than the polar specific algorithms. That's a big difference. And when we look at kind of what the global algorithm thinks is an atmospheric river, we get these kind of shapes seen here that are highlighted in these various colors. And a lot of them are kind of the moisture streaming from the west to the east, but we're not so interested in that. We want to know where the moisture is coming from the north to the south, almost in a straight line right into the continent. These are these very intense moisture intrusion events we wanted to study. And this is important because Antarctica, it is often surrounded by these sort of extratropical cyclones. And every cyclone has some moisture transport associated with it, but we don't want to focus on detecting every single time one of these storms occurs, which is, well, very often around Antarctica. We need to detect very unique events where you can see streams of clouds coming directly from the mid-latitudes right onto the continent. So with that, we need to first define our domain. So the areas in red here are the areas where we kind of care to detect the atmospheric rivers. So we have the Antarctic domain here and the Arctic domain here. And then we need to create a threshold, basically a value that says if we exceed this moisture content or this value of moisture transport in the atmosphere, then start paying attention to that and see if that could potentially be an atmospheric river. And so we have these terms defined here. IWV, or the integrated water vapor, it's just the vertical integral of a specific community. And then we also use the VIVT, which is the moisture transport in the atmosphere, but just using the V component of the wind. So basically tracking moisture that goes from north to south. And so we define these values and then compile them every 3 hour or 6 hour time step from during a study period, so from 1979 to 2020. And we define the 98th percentile for every location on this map and define it on a monthly basis. And so once we have our threshold, we can tell our algorithm to look for when these values form coherent shapes. So we train the algorithm to look for these things in continuous meridional direction. And we say it has to extend at least 20 degrees latitude. The algorithm has primarily been trained using reanalysis data from ERA 2 or ERA 5, but we have tested it on multiple reanalysis products and it does work. And so the algorithm does its job and it outputs these shapes that we can track in a Lagrangian perspective. So we track them through time and space. So we get these little shapes and we can see when and where they are at any given point during our study period. And this algorithm has been proven to be quite robust. It's a member of the ARTMIP project, which is this group seeking to obtain multiple people's detection algorithms for detecting atmospheric rivers, and they compare them to each other. So it has been sort of accepted into a broader community. So that's great. Now we have a tool for detecting the atmospheric rivers. That's just one part. We still need a tool then for how we can measure snowfall, precipitation, and melting on the Antarctic continent. So for that, I have to thank the folk here at the IGE and the folk at the University of Liège and their work in creating a regional climate model referred to as MAR. And MAR is different than your standard atmospheric reanalysis product in that it has actually a snow-specific model called Crocus that does a better job of resolving snow processes at the surface. such as the sublimation of airborne snow particles. And the model also has specifications for improving the physics of depicting the boundary layer, such as the katabatic wind or the stable boundary layer. Now, the MAR model has been shown to be a much more accurate tool at simulating precipitation compared to other reanalysis products. So it's a great thing to use in combination with our detection algorithm to begin studying the effects of rivers on the Antarctic continent. So with that said, let's go into some results after some tea. So with the atmospheric river climatology, with the atmospheric river detection algorithm, first thing we can do is make a climatology of the atmospheric rivers. So here we're looking at the annual frequency of atmospheric rivers around the continent from 1980 to 2018. And the colors here are their frequency of occurrence and percentage of all time steps. So they occur around 1% of all the time, and most commonly around the coastal parts of Antarctica. And this kind of translates to about, so any coastal point on the continent will have river conditions 2 or 3 days per year. So first off, right away, that's not much. That's very rare for something to study. And our algorithm is definitely much more stingy about detecting atmospheric rivers compared to here the Grenoble global detection algorithm. Here, this is work that is currently in progress, comparing the algorithms. And we see the Grenoble algorithm looking at the annual AR frequency in the era 5, detects the rivers about almost 10%, well, maybe 8-10% of the time around the Antarctic coastline. Whereas our algorithm barely gets up to about 1% of the time. So it's clear that these two algorithms are looking at very different things. And I think is that ours is more focused on the more meridional components of moisture transport. So with going into further with this climatology, we see that the ARs, the atmospheric rivers, the amount of rivers per year has been increasing in this part of the Antarctic continent. So on average, we've had about 0.5, one more detections per year from 1980 to 2018. Now, this is also the region where we had that very high snowfall events in 2009 and 2011. That's very curious. But these increases in detection actually pales in comparison to the overall variability of atmospheric rivers on a year-to-year basis around the Antarctic continent. So here we're looking at the standard deviation of atmospheric river detection, and here we have from values of 0 to 20. And really, like the standard deviation values gets up to around sometimes 10, 15, 20 per year, which basically is saying that some years you can have loads of AR activity, and then the next year it could be bust. So it's a very fickle thing to study. And then we want to look more into what kind of controls the track, the behavior of the atmospheric rivers. And so for this, in this example here, we're looking at the geopotential height anomalies at 500 hectopascal, so the mid-level of the atmosphere. And we want to see what the anomaly is every time there was an atmospheric river that made landfall up here on the Antarctic Peninsula. And right away, we get this very distinct pattern. We have a very pronounced blocking high pressure here and a trough sitting downstream of the landfall location. Now, this is true for the Antarctic Peninsula, but if we were to choose a point anywhere on the coast of Antarctica, you would have the same couplet, just moved in a different location. And in fact, the average distance between these couplets is about just 21 degrees latitude, and they typically are occurring at 63 degrees south. So we can actually kind of track these features in relation to the landfall locations. So that's kind of finishing up the climatology. And I think the most notable statistic from this part is that 3.2 days, that's about the most annual frequency we have of ARs on the continent, and that happens in the peninsula. So yes, they are pretty rare. So with the climatology, now we can actually start getting into our mass balance problem. So first, we want to look at the more of the surface melting on the continent. And in this part of the presentation, we'll show results from this paper here, tracking surface melt in West Antarctica. It was published in Nature Geoscience. So going back to my favorite event, January of 2016, we see here, we have plotted the values of vapor transport and integrated water vapor. And we're seeing how the two atmospheric river detection algorithms follow these events. And yes, so during this event, we have both algorithms detecting a river making landfall in West Antarctica, at very high values of vapor transport and high values of integrated water vapor. But what's actually causing the melting, though, is the amount of liquid water that is in the clouds. So this event had a very impressive amount of liquid water over the continent. When you have liquid water over an ice sheet, it becomes a very radiative cloud that actually transports radiation to the surface, and here in the form of downward long wave radiation. And that increases the temperature, which can be your melt trigger. And sure enough, during this event, during this about week and a half period, we see that melt was quite widespread around Antarctica. But that's just one event. These sort of large scale melt events that kind of have a signature like this, they're pretty rare. They've happened maybe 4 or 5 times since 1980. So to see if their atmospheric rivers were involved in these other events, we decided to look at every atmospheric river that makes landfall around this part of Antarctica here from 1979 to 2017. And we see what melt happened at the time of these landfalls. And then we compare it against all the melt that we recorded during this time period. And what we found is that almost all the melt that happened in the higher up parts of Antarctica could be attributed to an atmospheric river landfall. And a majority of the melt on the ice shelf here, so lower elevation, could also be attributed to the ARs. And this is true during the summer. During the winter, though, we focused on the Antarctic Peninsula here, where you would not expect melt to happen. It's cold, it's the winter, it's very dark. But when we found this, when these ARs made landfall on the mountain ranges here, they created a warming downsloping wind called the Föhn wind, which I'll get into more later in this presentation. But that wind actually also created a very high percentage of melting on the peninsula. Now, expanding this figure just a bit. So now we're looking at the composite of each of these atmospheric river landfalls and tracking their variables as we progress with time. So here we have point C, this is the point of the coast here. And so here you have the atmospheric river, and we see what happens up to 5 days after the landfall occurs. So typically, when you have your landfall, you have an increase in your vapor transport and your water vapor content, as expected, and the melt increases following that. Now, for the things that controlling the melt, when you have your river landfall, you have an increase in the water content of the clouds, following an increase in the downward long wave radiation. Then we go further inland, we see something similar, but instead, what's interesting is that you have your landfall and you have the increase in your moisture content, but the moisture remains elevated over this part of the continent, even after the AR has dissipated and moved out, because the AR landfall, only lasts about 1 to 2 days. But even after it disappears, melting can still occur as long as the moisture remains. And as long as that moisture remains, you can have long wave radiation and trigger melt. As for the Antarctic Peninsula, it's a pretty similar story, but the main difference is that you have an increase in the sensible heat flux, which is related to that Föhn effect. So that's another element causing melt in that region. But perhaps the biggest takeaway from the study is that melt might be rare today, but that might change in the future. So when we look at the 2-meter temperature anomalies, when we had these melting events on the Antarctic, Western Antarctic here, so remember about 4 or 5 of these occurred over our 40-year study period. They had this temperature anomaly profile, so getting up to around 6 degrees warmer than average. But we also did the same thing, but for every atmospheric river that made landfall in this part of the continent during a study period. Now, the rivers are much more common than the melting events. On average, you have 1 or 2 of these things making landfall per summer. So the vast majority of them do not cause melting. But what we found is that the difference between the temperature anomalies of your average atmospheric river landfall and the temperature anomalies between you actually having large scale melt on the West Antarctica is actually quite small. It's about 1-2 degrees. So that's saying that if the background temperature were to increase by 1-2 degrees, which is widely expected because of global warming, then all of a sudden your average atmospheric river will trigger melt at West Antarctica, which could become much more problematic in the future. So that actually is the most notable statistic from, I would say, this part of the study. 1-2 degrees is what's separating us from having, on average, a non-melting situation for a river landfall versus a melt-provoking situation for a river landfall. So this is covering the surface melt part. And now I want to move on, though, to ice shelf collapse, because this is more related to ice discharge. And as an example of this, here we're looking at the Larsen B ice shelf in 2002, which was a very catastrophic collapse of the ice shelf. Prior to its collapse, we had extensive melt pond formation along the ice shelf, a bunch of swimming pools setting up here. And these melt ponds really actually act to destabilize the ice shelf. The water sits on the ice shelf. It causes fractures in the ice that penetrate through the ice layer. And then once you have enough of these fractures, the whole thing can just give out and collapse dramatically, like we observed in 2002. And whereas for the previous study, where we observed surface melt in West Antarctica, that melt might just occur and refreeze back into the ice pack, thus not being a big deal. But when this ice disappears, all of a sudden now all the ice stored in the glaciers up here can now freely flow into the ocean and become a big problem for sea level rise. So this study began with an observation. In early February of 2020, a new temperature record was set in Antarctica of 18.3 degrees at Esperanza Station, so on a tip over here. This actually beat the previous Antarctic-wide temperature record of 17.5 degrees from March 2015. But this event had already been studied and concluded to have been caused by an atmospheric river. So we were curious to see maybe if this more recent record was a similar situation. And sure enough, our guess was right. When we trained our detection algorithms, so using both versions of the one I developed for this study and also the one from Irina Gordoviskaya, they all detected a very pronounced atmospheric river hitting the Antarctic Peninsula. So that opened up a broader question. Has this happened before other major melting events? So we decided to train our algorithm to give us all the atmospheric river landfalls that happened in this blue shaded region here from 1980 to 2019. And then for every one of these landfalls, we collect all the variables that happened at the same time, so temperature, melt runoff. And we analyze and we collect this using a 7.5 kilometer version of the MAR, so the high resolution can take into account to the more complex topography of the region. Right away, one of our most pronounced results was that intensity actually makes a huge difference in the amount of runoff that occurs on the Antarctic Peninsula. So when we looked at the runoff that occurs in this blue shaded region here on the ice shelf, we found that when we separate the atmospheric rivers based on their intensity, as the intensity increases, by the time you get to the most powerful atmospheric river landfalls, as intensity here is measured by the maximum value of integrated vapor transport at the time of the landfall, the amount of runoff exponentially increases. So your most powerful atmospheric rivers can actually create, on average, 0.2 or 0.3 gigatons of runoff per every 3 hours. Now, how they actually are doing this, though, is we have to go back to see what's causing the melt. So on average, when you have an atmospheric river making landfall on the Antarctic Peninsula, wanted to see what percentage of all the extreme temperature values that occurred over a whole study period occurred at the same time as these landfalls. And almost all the extreme temperatures actually can be correlated with these river landfalls. Because you have extreme temperatures, you could also now you generate extreme values of runoff. So the most extreme values of runoff also can be correlated with the occurrence of atmospheric river landfalls. And how this is happening is that when we take the composite, so the average sensible heat flux on the Antarctic Peninsula, whenever you have an atmospheric river landfall, see a positive sensible heat flux along the ice shelf. So again, this is because of that Föhn effect, warming the surface as the air descends. And also you have the contribution of the downward long-wave radiation because you have clouds of high liquid water sitting over the ice. And this schematic here kind of summarizes the whole story of what we're talking about. So what happens is you have an atmospheric river, it makes landfall, and the air rises over the mountains and then descends adiabatically on the leeward side. Now, this adiabatic descent of the air creates a Föhn effect, and that combined with the radiative properties of the clouds leads to runoff that does not refreeze back into the ice pack. Instead, it forms melt ponds. Those ponds then create fractures, which then can cause the collapse of the ice shelf. Another important component here is the sea ice that sits off the ice shelf. For the sea ice actually protects the ice shelf from waves traversing the open ocean. So we wanted to see, okay, maybe the atmospheric rivers are also affecting the sea ice. Sure enough, they didn't. On average, when you have a very intense atmospheric river, we're looking at the 2-day change in sea ice fraction following an atmospheric river landfall. Here we have values of almost a 10% decrease. On average, you actually have a very large decrease just on the northern end of the Antarctic Peninsula here. And when we look at this region of the Antarctic Peninsula, we actually found that almost all the largest 2-day decreases in sea ice extent occurred when an atmospheric river was in the area. So this is really important because now we've both shown that atmospheric rivers can precondition the ice shelves for collapse, and they also can help trigger the final collapse by removing the sea ice barrier. And in fact, this is not just theory, it's happened. Going back into our catalog of atmospheric rivers, we found that the collapse of the Larsen A ice shelf correlated with very strong atmospheric rivers. And also the collapse of the Larsen B ice shelf was correlated with a series of strong atmospheric rivers. As we can see here, the temperature profile and was correlated with the average AR activity in 2002. And now we have the Larsen C ice shelf, which is still there, but I think as a great risk of this phenomenon. So just an example to show what this actually looks like. Here we take the most extreme, actually this was the most powerful atmospheric river we observed in our study period. Made landfall in January of 2008. And here we have what now sea ice has taken over what was left of the Larsen A and Larsen B ice shelf. And then 1 day later, you have the atmospheric river make landfall. You can really see it well here. And then right after the landfall, you can see the sea ice has been destroyed in this area. It's been turned to Swiss cheese. And this event really led to a massive amount of runoff on the whole entirety of the Antarctic Peninsula. And we see the same profile when looking at the Larsen A collapse and the Larsen B collapse. So I would say the most notable statistics from this part would be 6.5 gigatons. That was the amount of runoff caused by the river that occurred in January of 1995. That river had a maximum intensity of 140 kilograms per meter per second. So going on to the final component now of our surface, of our mass balance, we wanted to see how they impact precipitation patterns. So this study begins first with the collaboration of John Turner, where we wanted to see, knowing that Antarctica is a desert, want to see how much the annual precipitation is controlled by just a few very high precipitation events during the year. And in that work, we found that large areas of Antarctica actually get most of their precipitation from just a very few extreme precipitation events or high precipitation events per year. The next question is, okay, what was causing those high precipitation events? Were they related to atmospheric rivers? So to get into this question, we go back to our AR detection algorithm. So here we're looking at a map of snowfall, and the red outline here is the shape of the atmospheric river. So for this study, we take all the snowfall that occurs within the footprint of an atmospheric river, and we do this for every atmospheric river that we detected, and we make a climatology of that. And we collect this data using a 35-kilometer version of the MAR from 1980 to 2018. And what we found is that about looking at the percentage of snowfall that could be attributed to atmospheric rivers, about 10-20% of all the snowfall that happened around East Antarctica could be attributed to the atmospheric rivers. Now, this snowfall profile looks like you have most of the snowfall along the coastline, which is expected. But we're more interested, though, in seeing in these really extreme precipitation events, these high precipitation events. When we looked at the 99th percentile of precipitation, so only the heaviest precipitation rates, we found that the atmospheric rivers were responsible for almost 60 to 70% of all of that precipitation. So that answers that question. We find that the ARs are causing most of the high precipitation events on the Antarctic continent, especially in East Antarctica. We also know that Antarctica has some trends in snowfall accumulation. So we wanted to see if the ARs were related to that. So we have our trends in annual atmospheric river frequencies seen here. We have a positive increase in Joining Moreland, a slight decrease in Wilkes Land and the Amundsen Sea coast. There are similar trends in snowfall at the same time. And we find that most of these trends can actually be explained by the snowfall caused by atmospheric rivers. So they control the trend as well. And then we want to look at one last part to see if the year-to-year variability of snowfall is actually being impacted by the rivers. And what we found is that, in fact, when we looked at the correlation between annual atmospheric river frequency and annual snowfall accumulation, the R-Pearson correlation between these two variables is actually significant, 0.05 to 0.75 over most of Antarctica, actually. And even the same can be said for rainfall on the tip of the Antarctic Peninsula. So we know now that the atmospheric rivers control the high precipitation events. They're controlling trends in snowfall on the continent, and they even control the year-to-year variability of snowfall. So they're a big deal. And we compile all the snowfall that happens below 1,500 meters on the Antarctic continent. We can say that 9 to 10% of that occurred because of atmospheric rivers. So to conclude basically the results of this research, we find that the atmospheric rivers are rare, but despite their rarity, their impacts are oversized and dramatic. Looking at the components of the mass balance, we see they cause surface melt in West Antarctica. They've caused ice shelf collapse on the Antarctic Peninsula. And they actually are controlling snowfall patterns around East Antarctica. And for now, we can say that this is a net positive for the Antarctic surface mass balance, but will this hold for the future? This is not known yet. So everything I've done in this PhD, I've concluded with I've developed an algorithm for detecting atmospheric rivers. During this PhD, I've created the first climatology of atmospheric rivers in Antarctica. And we demonstrated how these really short extreme events have a huge impact on the mean climate. And that, in fact, when studying moisture transport to the continent and moisture intrusions, the atmospheric rivers are very important and should be, I think, focused on more research when kind of looking into these questions. And I recommend for more of the community to kind of focus on this because it is such an important thing to examine. So that's the end of my research, but this PhD research is honestly open up more questions than is answered. For instance, how have atmospheric rivers changed in the past? Here, looking at snowfall, again, at Mount Brown South, this is actually an ice core drilling site. And with this project with the University of Tasmania, we want to see if the atmospheric river signal can be found within the ice core, because we expect the atmospheric rivers to have a bias in the delta O18 isotope because they are warm systems. We want to look at the future climate. How will the atmospheric rivers in Antarctica change in a warming climate? I mean, it's already been studied that in the future, using the Gordon-Walliser algorithm here, that atmospheric rivers will become more frequent in the Southern Ocean. But this is with the global algorithm. We need to apply the algorithm here to these same climate models to answer this question and see whether it is the thermodynamics of the atmosphere or circulation that will be the main influence on future behavior, and how that actually then translates to impacts on the mass balance of the continent. And I mean, there's just so much to study with this. I mean, research has already come out showing that the atmospheric rivers can cause disintegration of the sea ice. And sea ice is even important for the penguins because sea ice disintegration can actually help the penguins. But at the same time, if you have a lot of rainfall or snowfall on penguins, that can also lead to penguin colony collapse. So I'm happy to say that with all these questions, I'm not going anywhere. We have a new project funded from the ANR called ARCA, where I'll be doing a postdoc here in Grenoble. We'll be answering these questions. We want to know how atmospheric rivers will change in the future. To do that, we need to first understand how they can be measured today and maybe recorded in ice cores showing the past climate. So I'm very excited to embark on this project after this PhD. And during my PhD, I've established numerous collaborations with other people on this similar atmospheric river topic. I'm working on studying atmospheric rivers and related melt in Greenland. Like I said, we're working to retrieve the river signal and impacts on the ice cores from Dome and Mount Brown South with the folk from the University of Tasmania. Want to study more their effects on the surface mass balance with people from the University of Colorado. And working within the RMIP community, we'll continue to see how the choice in atmospheric river detection algorithm actually impacts how we determine their impacts are. So after all that, I really want to thank everyone who's helped me in this PhD. I've just listed here all my co-authors, supervisors, friends who listen to me talk about these all my research over beers at bars, back when we could go to bars. I really want to thank even the administration at this building, because my French is terrible and they dealt with me for 3 years, helping me with all my mission orders, and they're just so nice. I want to thank the team of researchers and contractors at Dome, Antarctica, who helped me during my field season when I began this PhD. And especially I want to thank my supervisor, Vincent Favier, who really showed me the way of the mountains and also science. So with all that said, my presentation is done, and I will now take questions from the jury. Thank you.